So in the last video, got JSR and RTS working, which is jump to subroutine and return from subroutine. And I did have a few questions over the weirdness of the 6502 and why it pushes the stack pointer -1. Sorry, it pushes the program counter -1 onto the stack when you jump to a subroutine, and then when you return, it goes to the sets the program counter to that +1. Which just seems a bit odd because it seems like you're just doing this -1 and +1 for no reason, but maybe there was a reason internally why the hardware did that made it simpler. But it appears to me that I've implemented it that way, and it appears that that is correct. And all I could find out about it is, other than basically if we ended up attempting this on a real 6502, if we could get something where we could actually analyze the stack and the memory and find out what it was. I found this thing on an NES website, and it's talking about some kind of trick that they want to do with JSR and RTS, and saying, well, to do this you have to know exactly how it works. And it's basically saying the program counter, that when it jumps to a subroutine, it basically pushes the next instruction -1. So it's the program counter -1, and then when it pops it off, it goes to +1, and it says that it stores it in the same order that I've stored it in. So I would say this all appears to be totally correct. I was also looking at here about the stack pointer. This just says it stores the program counter and it pops the program counter. So this seems fine. What I've got is absolutely fine. So I think what I should do is just flesh out these tests some more for JSR and RTS, and also add the jump command as well. So jump is just go to a new place and not actually be able to go back to where you were. So it's quicker because it doesn't require you to push anything onto the stack. It doesn't require any stack space. So yeah, that's all good. So first thing I want to do, let's just check that this still works. Yep, so the JSR test still works. So this is this JSR and RTS here. One thing I could do is just add a little bit more to this test, is that when I've jumped to a subroutine and jumped back like I've done here, the stack pointer shouldn't have changed. So the CPU, because we pushed something onto the stack and then we popped it off. So the stack pointer here should be exactly the same as the stack pointer afterwards. So in theory that doesn't change anything, it just makes the test a bit better. Yeah, that's fine. And is there anything else we can add to this test? Yeah, so the other thing is, it basically says JSR does not affect the processor status flags, and RTS does not affect the processor status flags. Oh, but I am doing a little LDA in here just to get this test working. But I'd like to write some tests as well for that, to make sure that JSR and RTS don't affect the processor status flags, but I can't test that here because I have affected them with this instruction. So if I stopped here and did a break there, I would be able to test it, but because of the way I've written this test, I can't do it. So I'd like to do that as well. So let's do that. So this should be JSR does not affect the processor status. So if I just do a program that just does the JSR, just takes 6 cycles. Let's see. Yeah, this doesn't affect the A register. Stack pointer does change. But really what I want to be able to do is just test the processor status before and afterwards that they're saying. But because of the way I've done the processor status with these bit fields, I can't actually do that. Yeah, I've done them all as bit fields. So there's no easy way to just test all of these at once. What would be really nice is if I could do that, if I could just test processor status like this, because this won't compile because there is no member processor status. So I wonder, is it possible to make is it possible to make a processor status like union? So one with these flags. I don't do unions very often, but how do you do them? I don't remember. Do you do them like that? unions. I don't use these very often. Is that right? Is the syntax I've got there just right? Do I have to give it a name? Oh, it does compile. Oh, and it's even said it's passed. So in theory, this takes up the same. This only takes up 1 byte, but I'm just able to, like, I can access I there, and that should be the 3rd bit of this byte in theory, or has it not done it that way? That's very, I mean, I suppose we could just look in the debugger and work out what it's done. No, because that's not, that value should be, well, CC is not 0. So these things clearly aren't a union here. So that's not it. And in fact, this should, I bet this test passes as well, doesn't it? Oh no. Oh, it's made loads of tests fail doing that. The other data members are allocated in the same bytes as part of the largest member. Yeah, it feels like that's the way to do it. But it's not right. Oh, now I've got, yeah. So I've got a mega fail from that. So I don't really know the easy way, easy way around this that's going to make everything compile still without me having to change everything. Feels like it's this. Oh, Jesus. Feels like it's that. And in effect, I could then do that there. And that's fine, but I have PS if I want to access anything by bits now. So now this becomes like, I mean, maybe this, oh yeah, maybe this is not, oh no, there's a lot of errors there. And this looks just super ugly. Oh, but actually, yeah, this is ugly as you like. Let's just roll with it and see if it works. Because I think I'm going to need this anyway. And now weirdly, it can't actually compare the processor status byte. Oh, because it's actually processor status. Oh, it's just, that's going to be weird. Yeah, because it's going to be processor status. Let's roll with it for now, and we can rename it later. That's going to look horrible. That becomes that. Is that going to compile now? Yeah, well that that looks disgusting, but that's the way it is. So, does this pass the test? No, it doesn't. Oh dear. This is a miserable failure. This might be me reverting what I've done and starting again at this point. Why does this not work though? Is this union not doing what I think it's doing? That's not a union of that. Am I reading this wrong? That value should be the same as these values, and it's not. Oh, have I just done this wrong? Oh yeah, I'm reading the wrong thing. Feels like I should have just done it as does feel like it's this, but this wasn't right either. At least it won't have the horrible syntax. Oh, that's compiling. Oh my god, no. No, that doesn't work. What is the deal? What is the deal? Why are you so hard, unions? Why can't you make a union? So this is not a union of that. Why is it not a union? No, it's just got a different value in there. What is the deal with you, processor status? So clearly I don't know how to make a union. I don't do them very often, but when I do, I get this horrible thing going on here. I just want to know that, like, I've just put an extra value in there. I just want to see that those two are at least the same. Yeah, these two are the same, but maybe it doesn't work with bit fields. Do unions not work with bit fields? There's no mention of bit fields on here. Let's try this. So these are status flags. Okay. So they are just the bits. Are you going to let that compile? Yep. And then in here, I can do a union, an anonymous union of processor status. Oh, spell it right. And the flags have to have a name now. Oh, you press tab and it does something you didn't want. Right. This now won't compile. I think this is going to work. Except now this PS dot needs to be changed to bit's a bad word. Again, I can rename it later if this compiles. Does it compile? Yeah, it does. Now this, at least this gets nicer, because that's now actually the program, the processor status. Right. Have we actually achieved anything here? Let's just see to start with. Oh, was that a pass? It was. I think that's it. Oh my word. That was hard work. And I've got this horrible name now. So all I've really done there, just to go back to it, is I've made a struct called status flags, which just contains bit fields. And I've made a union of those bit fields with a single byte, which is the processor status. And the reason is because sometimes I want to treat this processor status as a byte, and sometimes I just want to access the bits. And I've had to call this thing bit, which is a bad name, but I could rename this to flag maybe. Let's just do that. So it becomes like, yeah, this is the processor status flag, and that's the whole byte. I think I'm actually missing, if I look at it here, I think there's actually an unused bit. because there's only 1, 2, 3, 4, 5, 6. There's only 7 bits in here. I think one of these bits is actually not set. Status register has 8 flags. A flag of something indicates whether something has or has not occurred. Bits of this register alter depending on the result of arithmetic. So yeah, it's bit 5 is not set. So actually I do need to put these in a specific order. And in fact, it's the order I've got them there, is it? D, B, V, and they're calling that S, which is sign flag. I'm calling it N for negative. So I'm just missing the unused bit, which is after the B. There we go. So that's just for completeness, to make sure that these status flags actually match up with what the processor had. And that's just in case that if I wanted to emulate a program and it happened to be like reading the processor, the status register, and pulling a bit out somewhere, if it did happen to do that, if I had these in the wrong order, or I hadn't put that unused one in, they could come out in the wrong order. I don't think it's going to affect this program because that's still going to pass. But that's good because our program still has to pass. So now all that nonsense is over. We're back to kind of where we started, except now we know that the processor, we've got an extra check in here. We now know that the processor status didn't change before and afterwards. And we can have just a quick look in there to see that, yeah. So we've got our zeros in there, and it should match up with that. I don't know if we can see it just before we go in. Should be a bunch of nonsense in here. Yeah, look, CC is uninitialized stack memory because I haven't initialized this yet. And it's got all kinds of crazy things in there, which is what I'd expect if it was CC, I think, is it? It is CC. So yeah. So in effect, that should be, yeah, it kind of should match up. 11001100. Yep. So that does match up. Yeah, that does match. So we have made a proper union now. Phew. So back to the task at hand. So we've got a better test now. We've tested that JSR does not affect the processor status. That's good. We could also test maybe that RTS also doesn't affect the processor status, because if we did, let's just do our original test where we do the RTS up here. So let's do that. The RTS is also 6 cycles, I believe. So all we did there is we jumped to a subroutine, and then all the subroutine did was return from the subroutine. We still expect that the processor status has not changed. So I would expect that to pass as well, I think. Jumps and calls, there you go. RTS does not affect the processor status, JSR does not affect the processor status. And we can jump to a subroutine and back again. And we're also testing that the process, yeah, we're testing that the processor status, yeah, we're testing that the stack pointer isn't affected on that one, because by the time you've got back, it should be different. I mean, in some of these as well, we can expect that once a JSR happens, that the stack pointer, we've got PS for processor status and SP for stack pointer. That's not confusing, is it? We can expect that the stack pointer is not equal, because if it is, we won't know where to get back to. So that can't be the same after a JSR and the RTS hasn't occurred yet. So that still passes, so that's a good sign. So we're getting a bit further now. So let's try and do the jump. So does jump affect the processor status either? It does not. So can jump do new. Cool. So this is jump. We're going to jump to 8,000 again, and we won't do anything when we get there. Is jump 6 cycles? It is. Oh, we've got 2 addressing modes. Oh, we've got absolute, which is just kind of what I did there. So this is jump absolute. Jump absolute. Oh, 3 cycles. That's a quickie. And again, we expect, it only took 3 cycles, we expect the processor status not to be changed. We expect now the stack pointer not to be changed, because this should not push onto the stack, because it doesn't need to. It just literally sets the program counter. So almost nothing changes on this one. And then what's the indirect one? Indirect. Oh, jump is the only 6502 instruction to support indirection. Wow. The instruction contains a 16-bit address which identifies the location of the least significant byte of another 16-bit memory address. Wow. So yeah, so it contains a full address that has the pointer to another address. And I assume we jump to that one. So let's do that one. That's a 5-cycle one. So I suppose that's so you can have like a jump table, and I think that's what the kernel does actually. The kernel has a jump table of whenever you call a method in the kernel, like in the Commodore 64, it doesn't actually call the method directly. It jumps to the jump table, which then jumps to the place in the kernel. And the reason you do that is in case they do a different kernel and they can put the stuff in a different place. And that's basically what a virtual function table is in C++ as well. It's just a table of pointers to functions. So weirdly, the kernel in the Commodore 64 and the C++ class are kind of the same thing. So the kernel is like a whole class. It's even got virtual functions in it. There you go, C++, it's not a new thing. Jump indirect. Indirect. This is a 5-cycle thing. That's just indirect. And so we want to we read the 16-bit address of something, and then at that 16-bit address, which remember is 8000, 8001, there is another address. Wow. So we'll jump to 9000 after that. So in effect, this just jumps the program counter to 9000. So again, we expect processor status not to change, stack pointer shouldn't change. We expect that the program counter will be at 9000. It's going to jump straight there. Yeah, we expect you to be bang on where you're supposed to be. And in fact, we can test that in this one as well. We're expected to be at 8000 in that one. I won't test the program counter in this one. Or should I? No, let's leave that one. Could I? I'm expecting to be at, after I return from the subroutine, I would expect the program counter to be at, yeah, I could actually test it on that one as well. I expect the program counter to be at the instruction after that one, because we return from there, we're going to do the instruction afterwards. This one didn't return, so does it matter too much at that point? Maybe it does. No, because we stopped. Oh yeah, we expect the program counter to be at 8000 on that one, because it's jumped into the subroutine. So that we can expect. And this one, we don't care about that one, because if it jumped back, we know we just executed a function to know that we jumped back. So that's pretty cool. Right, what have we got that fails in here now? We need to define these these instruction opcodes. So opcodes, two opcodes. So we've got jump absolute, and we've got jump indirect. Right, yeah. So jump absolute 4C and jump indirect 6C. So we should have a few failing tests there, I think. Two failing tests. We got jump absolute and jump indirect because we haven't written those. which is pretty cool. And the other ones seem to have passed. So those extra tests that I added have probably worked. There's also a note here. An original 6502 does not correctly fetch the target address if the indirect vector falls on a page boundary. Oh dear. This is fixed on some later chips. Oh, we'd have to make a note of that. So that might be where we need to add some new tests. But it's basically saying that sometimes it's broken. Now, again, it depends. This depends on which 6502 you want to emulate, because there was probably quite a few of them. So I like, if you wanted to do the 6510 that was in the Commodore 64, I wonder if this did that. This might be where you have to test to make sure. But maybe just no one did this because they didn't know if it was going to work like that. I'll make a note of this in the code and we won't handle this for now. So we've got JSR, we've got RTS. We need jump indirect. And let's do the easy one first, jump absolute. So we just read, for this we just read an address off there, and we're going to set the program counter to the address. And again, we need to consume the correct number of cycles, which is 3, which actually works out here because I think it's 1 to read the instruction and 2 to read the address, and then that's it. Let's just check that works. And it did. So we've got a jump absolute. And then jump indirect is kind of the same, except you read an address from memory and then you take that address and then you read a word from that address. We've got read word from the address from memory, and we set that back to the address. So there's your indirection there. That's basically how a virtual function works. Is that it's pointed to a pointer, which is what we had there, and then we set it there. I think that's going to work out as well because the extra 2 cycles is taken up by the 1 to read the byte, 2 to read the address, and then 2 to read another address. It gives you 5. And is that going to pass? And it does. So that is really cool. So I've improved the tests and I've basically implemented the jumps and calls. JMP, JSR and RTS are basically working. So we've now got a 6502. Oh, actually, let's put this note in though. Okay, so I've made a note of that. So yeah, we've got a 6502 now that can read from memory into registers, write from registers into memory, and can jump around a little bit in the program. That would allow writing of like a small program that could copy memory, I suppose. You could write a mem copy with that maybe. You can't really loop or branch on conditions yet, so that's all a bit odd. And I think I spent longer messing around with this union nonsense that I'd forgotten how to do. But I think we're better off for it here anyway, because now when you read these flags, you read them like that, flag C. So that kind of reads okay. It's a bit more wordy than it was before, but it's not too bad. So I'm not too unhappy about that. But this is definitely better already, that the process is, because there is actually, I think maybe we could do the stack functions next, because there is ways I think there's functions that pushes the processor status onto the stack, and you do that as a byte. So this would just be able to just push this, and that would be done. We'll get to all this in the next video when I do even more instructions. And a quick count, how many have we done? 35 instructions. I've got 35 working instructions. It's a miracle. I've still got more to do than I've done, and probably some harder ones than I've done already. But I have a CPU that can do 35 different things, probably. I think I'm quite happy with that so far. I don't know if I'm going to be really unhappy with it when I get a bit further, but I'm quite confident that it's working correctly, so cool. So get to it in the next video.